Today we're going to talk about analog and digital sound. If you have a look at the images on the screen there, you can see on your left hand side you've got the old album, the record that I grew up with, okay, so the vinyl. In the middle you've got your CD. You don't see as many CDs today, and the MP3 player, and most of the sounds you hear today are MP3. So which is the better quality sound? Well, it has to be said that the vinyl, the record that you see on your left, is pure sound. So I suppose you could say that that's the better quality sound because it is pure. Now when we talk about pure sound, we're talking about analog sound. This is one continuous sound wave, and it is a true representation of a sound. So when I sing into a microphone, which I'm not going to do because you'll all leave the video, it's exactly what's written onto a vinyl record. Okay, so when you sing into a microphone, that's pure sound, and that's what would go onto a vinyl record. Okay, now digital sound is a little bit different in that it's not a true sound. It's not the actual sound you are hearing, but rather a combination of binary code. Okay, so digital isn't the actual sound, but samples of the sound placed together to create a true likeness of the original sound. The advantages of this is there's not as much interference. It can also be edited really easily, whereas the analog sound couldn't, and copies can be made over and over again without losing the quality. So digital sound has a lot going for it. Disadvantages are it isn't a true representation of the original sound, and quality could be lost depending on the recording. Okay, so digital versus analog. Here we go, these are the sound waves. We've got the analog sound signals which are continuous, and we've got the digital signals which are discrete. They're made up individually of different samples, and we're going to look at samples later. So the analog, to convert analog to digital, we have to use a converter, an analog to digital converter. So when somebody is talking into a mic like myself, the computer takes that sound and converts it into something that it understands. So it digitally converts it. Okay. Now what we see here is an analog sound wave. Okay, you can see on the left hand side we have the bit depth, the resolution, and on the bottom we see the time in seconds. So the bottom x-axis is the time in seconds, and the y-axis is the resolution bit depth. If we have a look at recording A, we can see that the bit depth, or the resolution, goes up to 7. It's got 8 points if you include the 0. Here we go. So this is 0 to 7. Okay. Now on the bottom we've got the 3 seconds on the x-axis, the time in seconds. We've got 3 seconds here. Okay. And in each second we have 6 samples of the sound. Now we can work out that we need 3 bits per sample. Now to do this we have to remember binary. If you have a look at the resolution, the bit depth, we can see that we have 7 on our resolution. Okay, so what we have to do is we have to think about our binary numbers. Okay, and you can see the first 3 are highlighted in yellow. If you add these together, they come up to the number 7. So we know we only need 3 bits. These are all bits. If we had all of them, there's 8 bits there. But we only need 3, the 3 that are highlighted. And 4 plus 2 plus 1 equals 7. Okay. If I had any more on the bit depth on the left hand side, then obviously we'd need more bits. but we only need 3 for this recording. Okay, so we have 6 samples per second. We have 6 samples per second over 3 seconds. So that's 6 times 3, that's 18 samples altogether. Okay, so if we go right across here, we can calculate 18 samples of sound. So 18 times the 3 bits is 54 bits. If we look at recording B, we can see the resolution has 16 points this time, so starting from 0 up to 15. Okay, here we go, that's the resolution, the bit depth. Okay, and we have 3 seconds on the x-axis. 3 samples per second, so instead of the 6 samples we've got 3 samples, and this time we're going to go for 4 bits per sample because we have now 15 on our resolution. So if we go back to our binary, okay, we have up to 15 on our resolution. Put in the binary numbers that we remember, and working from the right to the left, we can see if we add 8 plus 4 plus 2 plus 1 together, we get 15. So we only need 4 bits. If we had any higher than 15, obviously we'd go on to the 5 bits and so on. Okay, but in this example we've only got 15, so we only need 4 bits. So 3 samples per second over 3 seconds, that's 9 samples altogether. So if we calculate all them, 9 samples. So 9 times the 4 bits is 36 bits. If we go to recording C, this still has a resolution of 16 points, so 0 to 15 here. Okay, and 3 seconds on the axis still. And this time we've increased it to 6 samples per second. So 4 bits per sample. We're using 4 bits, remember, because of our binary. Okay, we've got 15 on our resolution. Put our numbers there, and if we total 8 plus 4 plus 2 plus 1, we have the 15. So we know we only need 4 bits per sample. Okay, so 6 samples per second. Over 3 seconds we have 18 samples, so 6 times 3 is 18 samples. So 18 times 4 bits is 72 bits. So which will have the highest quality? Well, we have to remember we are looking at the bit depth, so the higher the bit depth, then the higher quality, and the more samples we have per second, the higher the quality. So recording C has the highest resolution and samples are taken more frequently, so this is going to be the highest quality. So state a device that is used to capture an analog sound signal. I'm using one now, a microphone. Okay. The length of recording will heavily influence the size of the sound file. State 2 factors other than recording length that determines the file size of the recording. We said that earlier. The sample rate, how many samples you take per second. Okay, the sample rate, how many samples have been taken per second. The higher the sample rate, the higher the quality, the more sound you have captured. Also the resolution, the bit depth. The bit depth is the number of bits available for each sample. The higher the bit depth, the higher the quality of the audio. And draw a line to match each file. Here we've done the code for you, so MP3 file, an audio coding format which uses a form of lossy data compression. MP4, a digital multimedia format most commonly used to store video and audio. A WAV file, an audio file format used for raw and typically uncompressed audio. MIDI, a set of instructions for digital instruments to play synthesized sounds. JPEG file is a commonly used image format used by digital cameras. Just to recap, the bit depth, number of bits available for each sample. The bit rate is the number of bits used to store a second of sampled sound. And sample rate, the number of times the sound is sampled per second. So to measure a bit rate, we take the bit depth times that by the sample rate.